All right, let's go ahead and get started. Welcome to 3.4 Part 1. This section will be a couple videos long. 3.5 will be a little bit longer, but it shouldn't be too bad. So in this section, we're looking at polynomial functions, graphs, applications, and models. For 3.4, we're mostly looking at how these graphs look, how, different polynomials, right? Different exponents, x to the fourth, x to the fifth, and so on. And we're going to look at like how they turn and how they behave as far as their graphs go, okay? We've practiced like their parent functions, like we've graphed y equals x cubed, so we want to see how that moves around and how it looks. So a couple of things. Turning points, that's a term. Sometimes you'll hear in other classes, you'll hear inflection points. But essentially this is where you hear, where you see a function go from increasing, so a change in a function's increasing or decreasing behavior. So essentially we're looking at where the function turns from going down to up and up to down. Okay? So if you looked right here, there's not a good example on this one, but essentially if you think of a loop, kind of, you see where it would go from up to going down, that would be a turning point. Okay? Something like this. So this would be increasing, down to decreasing. That's where it switches, right? So that would be a turning point. End behavior is the behavior of a function as x goes to infinity or x goes to negative infinity. So it's really obvious what it kind of means by the name, right? End behavior, I can zoom in a little bit. End behavior just means what is the function doing as it continues on. So for example, looking at this one right here, the end behavior of this function y equals x is as it goes on forever, as x continues on forever this way. What is it going to do? Well, it's going to keep going up. It's going to keep increasing, right? And as x goes to negative infinity, what's it going to do this way? Well, it's going to keep going down. Okay? So you kind of, even though we didn't draw this going on forever, you're kind of getting a look at what's that function going to do forever in its entirety of its existence. Okay? That's what end behavior kind of means here. And so let's go ahead and get started on this. So these are some basic graphs. These are the parent functions that look like they are odd here, right? We have x, x cubed, and x to the fifth. So each graph above is a odd function, first off. So it has an odd degree and is an odd function. We talked about what that means as far as symmetry means. Okay, it exhibits symmetry about the origin. That means that if you fold it over the origin along the line y equals x, you would have a symmetric function, right? Each one has domain. So think about it. Domain, it would be negative infinity to infinity. So all reals, and same with the range. Okay, all the y values would fit there. So negative infinity up to infinity. And they're continuous, right? I can draw this whole picture without picking my pencil up on the entire domain, which again was negative infinity up to infinity. Okay, on the other, additionally, these functions, okay, these are odd again, they're odd functions. These odd functions are increasing. So if you look at all of them, they get bigger. So increasing, I like to think of if I sat myself on this line right here, right here, and I walked from left to right, am I walking uphill or downhill? And this is pretty easy, right? I'm walking uphill the whole time. Here I'm walking uphill, slight uphill. Same here. They're all increasing on their entire domain, which is still infinity, infinity. And then they fall to the left. So if you go to the left, they fall, and they rise to the right. Okay? So the idea of this description is that if I told you all this, it's kind of like giving you directions to the store, right? I'm giving you a little bit of information about everything in this function, okay? I'm telling you they're odd, they're symmetric about the origin, they increase over their entire domain. If you look to the right, it's increasing or rising. You look to the left, it's falling down. You have a lot of information about that graph, and you can actually do this for all kinds of graphs. And so the idea is less important that you can get the exact graph, because we can do that anywhere, but it's more important that you know exactly what's happening as these graphs go on, okay? So let's do the same kind of little table for even functions here. Try to keep an eye on the time. So each one above, we have x squared, x to the fourth, and x to the sixth. Each one above has an even degree. So again, the degree is the exponent here, so 2, 4, and 6. And it's an even function, okay? So that has symmetry about the y-axis. Okay? And so what that means, right, if I fold over the y-axis, you get that same picture, okay? Each one's domain is certainly negative infinity to infinity, right? You can put any x value in there. But the range on these ones is starting at 0 and going up to infinity, 0 inclusive, right? So this is where when you move this around, you're going to get kind of a tricky spot with that range, okay? Now, these functions are continuous. Again, they're even functions. On their entire domain, again, I can draw each one of these without picking up my pencil. And so the domain is negative infinity to infinity. However, they are decreasing. I don't know why, however, is the word they chose to use there. Decreasing from negative infinity to 0. So look at it. If I'm walking on that line from the negative infinity up to here, I'm walking downhill. And then at that turning point 0, I start to walk uphill. Okay? So they're increasing from here on out. Okay? Now, it looks like it appears that they rise on both the left and the right. So if you're looking to the left, it kind of goes up. If you're looking to the right, it goes up. That's less important than knowing where it's increasing and decreasing. So this is a really good, because most polynomial functions, actually all polynomial functions, can be split into either even or odd, right? As far as the degree goes. And so this will tell you a lot about all these kinds of polynomial functions. It tells you exactly what's happening, and it's a good descriptor of what is actually going on. Okay? And so now we can take all of these polynomial functions and we can actually flip them around and do different transformations on them. Okay? So first off, now we're looking at just the general ax to the n. So this can be positive, or this can be even or odd. Okay? So first off, when absolute value of a is greater than 1, we've talked about this, it gets stretched vertically. Okay? Making it narrower. So we've talked about that, right? If you think of x squared, 2x squared is a little bit steeper. Okay? Now when that's a fraction, when the absolute value that's a fraction, the graph is shrunk, or what would they use? Vertically compressed? Yeah. Vertically compressed. And he's making it wider, okay, or fatter. Think about 1/2 x squared, right? You take the x squared function, you squish it down a little bit, okay? Now, we're on to negative. That negative out front, okay, that is reflected across the x-axis. We've talked about that. Okay, and we've done all these transformations before, right? It doesn't change for the general polynomial at all. Okay. Now we have that plus k that's going to be shifted or translated k units up if k is positive, right? And k units down if k is negative. Maybe I want to put an absolute value there. Do they have that? They do. Okay. If k is negative, obviously you're going to move at positive units down. That makes a lot of sense. Okay. Now, if that h is on the inside, remember the k on the outside is up and down. If it's on the inside, it's left and right. So here we're gonna translate it h units, and remember it's the opposite of what you think. Okay. So if h is positive here, it's x minus h. That's gonna be h units to the right. If h is positive. Okay. Again, remember if x minus 2, you're moving it to the right, and it's gonna be absolute value of h units to the left if h is negative. Okay. So again, that's the opposite of what you think. Now, this one shows a combination of all of these, and these are all called, this one's translations, right? This is showing how they move left and right. So you can move it left and right, you can move it left and up, and then you could also, shrink it or stretch it. Okay, so we'll see all these in action a little bit. But the idea is going to be that we can look at the behavior of these functions based on those original 6 that we graphed, or in general all of them, and just kind of move them around a little bit. And so I'm going to really not do a whole lot of graphing. We'll see like the beginning of it, and then we'll do a lot of just like sketching from there. But it's not going to be too hard here. Okay. So the directions say graph each polynomial function, determine the largest open intervals of the domain over which each function is increasing or decreasing. That's it. Okay. So we want to get the biggest amount of time that they're increasing and decreasing. So, x cubed plus 1. Now you could make a table and graph that, right? Totally fine. You could use decimals, whatever you wanted to do. But we know what x cubed looks like, and this is just x cubed. X cubed translated up 1. That's all this is. And so we're going to draw the x cubed function, but we're going to move it up 1. So again, if you're following along at home, I'm looking at this one right here. That's the x cubed function right there. And so instead of 0, 0, I'm going to put it at 0, 1. Instead of at 1, 1, I'm going to put it at 1, 2. Instead of negative 1, negative 1, I'm going to put it at negative 1, 0. And then it's what, 2, 8, so it gets really big. So we'll kind of, well, it would be right here. So let's just draw it. How bad do I want it? Like this. Okay. Pretty rough. Those first 3 points are correct, obviously. And you could check for sure, right? Because 2 is going to be 9, so it's on the right way. But yeah, so there's that. Again, this is just x cubed moved up 1. Now, we want to know the largest open intervals over which it's increasing. Now, this is increasing, as we talked about, right? It's increasing over the entire domain, okay? So, increasing on negative infinity up to infinity, okay? Not decreasing anywhere, so that's good to go, okay? So, we're just going to be moving stuff around. Here we have x minus 2 to the 5th. Now, I'm looking at the x to the 5th function. That's over here. Wrong one. X to the 5th function right there, right? Okay, and again, like even on this picture, they didn't really graph it, right? They have 1, 1, they have negative 1, and 0, 0, and then they just kind of graph from there, right? But we're going to do the same thing, except for we're going to take ours and we're going to move it, x to the 5th moved, we're going to move it right 2. So instead of 0, 0, it's going to be 2, 0. Instead of 1, 1, it's going to be 3, 1. And instead of negative 1, it's going to be right there. And now they really squished it, right? So it comes down like this and hits here and it squishes and goes up. Okay? Not the best picture, but it gets the right idea. Now, it's that's a really bad picture. I looked at it twice. It should squish in the middle and then kind of go out, right? It looks similar to this, except for I'm not a good artist. Okay? Now, where is it increasing? Now, just like I said in the first page, it is still increasing on the entire domain. So we will put increasing on negative infinity up to infinity. Okay? Not decreasing anywhere. All right. On to the next one. We have a little bit more involved in this one. Okay? So it's negative 1/2 x plus 3 to the 4th plus 5. So this is a combination of things. Okay, so obviously this is just x to the 4th. It's going to be reflected. So a couple things here. Reflected across x-axis. Okay, that comes from the negative right here. It's going to be compressed by 1/2 here because of the 1/2. It's going to be moved left 3 and up 5. Okay, so we're still gonna do the kind of the same fluffy fluffy graphing that we just did, right? So we're gonna take this x to the 4th one right in the middle here, and see how they kind of just like graphed 1, 1, 0, 0, and negative 1, 1, and kind of just drew it. Looks a lot like the x to the 6th one, right? Looks a lot like it. It's a little bit fatter. Okay, we're gonna do the same thing, except for we're gonna do a couple things. So first off, instead of 0, 0, it's gonna be left 3, so 1, 2, 3, and up 5. Okay, so there's our vertex. Now instead of opening up, it's going to open down, right? And so it's also going to be compressed. And so instead of going from, in this case, instead of going from 1 to 1, it's going to go from 1 to 1/2, right? So, or even a little bit smaller than that. And so we're going to kind of just do that. We're just going to put it, instead of going this way, it's going to be really tubby right there. Okay? Just it's going to be compressed down a little bit. And so it's just going to look a little bit wider, not a lot, something like this. Okay? Now again, if you wanted the exact graph, which we are not getting from any of this, right? If you wanted the exact graph, what you could do is you could make the t-chart. But what we know here is you can tell me a lot about this function, right? You can tell me exactly where it goes, what it does, and you can actually make a pretty accurate graph based on that, right? If you give me, if you give me one more point, we can do all that without doing a whole lot of work here. So this tells us a lot about these functions without doing a lot of work, which is really, really useful. Okay? So let's see here. Unless otherwise restricted, The domain of all polynomial functions is going to be the set of all real numbers. Okay, we're going to do this, though. Set of all real numbers. I guess let's just put real numbers. They have 2 lines, huh? Okay. Polynomials are smooth continuous curves on the entire interval. So again, that's on the domain. In the range of all the odd ones, right? Just like in that first thing. Where to go? These are all the odd ones again, right? The range of that one is also the set of real numbers. Okay, and that's just in general. You should pick that up from the 3 examples that we did. Okay. Now, a polynomial function of even degree has the range of the form. Now, this is from 0 to infinity. Okay. Or k to infinity. For some real k. Now, it could be k to negative infinity as well, right? There's no reason that it couldn't be that, but this should be good enough for us. We should be happy with this. Okay? I got lost of where I was at, actually. All right. Is this a good point to stop? Maybe? It's what, been 16 minutes? Yeah, let's stop here. Okay, this is part 1. There's a couple more parts to 3.4, but that'll be the end of part 1.